In this lecture, we will use diodes to create mixers, and we know that diodes are very frequently used as switches in the circuits. So up till now, we have been using MOS as switches in the mixer circuit that we analyzed, but now we are going to use diode. Usually at very high frequency, it is diodes which are used as switches rather than the MOS. In addition to that, we will also see the mixer noise factor in general and relation of the mixer noise factor for down conversion mixer, that means in the receiver path, specifically for the two cases of the message, that is single sideband message and double sideband message. And we will see that there is a difference in the noise factor for the down conversion mixer for these two types of signals. For this diode switch mixers, we will consider two circuits, and these circuits are of course are going to be passive because we know that diode do not have amplifying capability. So first we will talk about single balance diode mixer. So in this case, only one of the ports is going to be balanced, and it is going to be the LO port. Rest of the two ports, that means the output or IF port, there and the RF port, they are going to be single-ended. So this is the architecture of a single balanced diode mixer. Now this architecture implementation requires two diodes. Transformer is required to implement this circuit. And it has 1:2 windings, such that number of windings between node A and B is same as that of the primary, and that between B and C is also same as that of primary. So these dots, they designate the polarity. So here we have a single valence diode mixer, and in this circuit, as was pointed out, D1 and D2, they act as switches. And since we want D1 and D2 to act as switches, we will see that it is LO which is responsible for switching them on or off. That means making them forward bias or reverse bias. So these two, so that is why VLO signal should be large. In fact, we are going to take a square wave for VLO. Like this. And VRF, as usual, is going to be a sinusoidal signal. So here also we will analyze this circuit for the two half of the LO. For the first half when it is high, and for the second half when VLO is low. And for each half we will try to see that what is the status of the two diodes, and then try to find out the output voltage by replacing the diodes with short circuit or open circuit. So here I would like to point out the relation between the LO input signal and voltage between node AB and node BC. So here, since transformer is 1:2 winding, so the voltage between A and B is going to be same as that of the input LO. So here VAB is equal to VLO, and VAB is nothing but VA minus VB is equal to VLO, and VA and VB is VRF. So we can see that VA will always be VRF plus VLO. So this is the story when say we have this polarity. In that case, A will also be at higher polarity, and similarly B will be higher at compared with C. So this is going to be the polarity of two halves of the secondary. So similarly for BC also, we can see that VBC is going to be VLO, and VB minus VC is equal to VLO, and VB is RF minus VC, VLO. So VC is going to be VRF minus VLO. So using this, we can find out the voltage at node A and C whenever required. Now let us try to find out the output. So first we will consider case 1. In this case, VLO is high. So VLO is high. That means what we have is this kind of polarity. That is, A is at higher polarity compared with C, and B is also higher compared with C. So now we need to know what will be the status of these two diodes. So what we find here is that since we have considered LO to be high, so VAC is going to be high voltage. So this implies VAC is positive or high. That means node A is at higher potential compared with node C. So what we see here is in this case, the network of D1 and D2, it experiences a voltage pressure or voltage slope in this direction, that is, which is reverse to the diode orientation. That means whenever VLO is high, these two diodes, they experience reverse bias. So for this case, this implies VAC in fact is going to be equal to 2 VLO. In fact, to be more precise, plus 2 VLO. So this implies D1 and D2 large reverse bias. So this is D1 and D2, they are going to be off. So if they are going to be off, then the equivalent circuit is now like this. So D1 is open circuited, D2 is also open circuited, and here we have our load. So this is a scenario. So here we can see that very clearly that V output is going to be equal to 0. Or this can be written as 0 into VRF. Now we consider the second case. That means LO is negative or low. So VLO is low. That means now we have reverse polarity for LO. I mean, this is at lower potential compared with this node. So polarity of this is also going to change now. So C is now going to be at higher potential compared with A. And B is going to be higher potential compared with A. So in this case, VAC is now going to be minus 2 VLO. So what happens now is, here we can see that orientation of the potential pressure or the potential gradient is going to be now in this direction. So here we see that these two diodes, they experience a large forward bias. So this is D1 and D2, they are going to be on. So is for this case, the equivalent circuit both D1 and D2, they are going to be closed switch. So now we have this polarity for the primary and secondary. So here we have already calculated A and C voltage, but this case is different. Now LO is low, so we can recalculate VAB as VLO, which is in fact negative. So VA is VB minus VLO. So this is equal to VRF minus VLO. Similarly, VBC is also negative, and VB is equal to VRF minus VC is equal to VLO. So here we see that VC is equal to VRF plus VLO. So now here we see is that node A is a series combination of two sources, and then this is also a series combination of two sources. So here we have two voltages. This is VRF and this is minus VLO, and here we again have two sources. One is VRF and other is VLO. So because of that, the voltage that we will see at the output is going to be VRF, because LO voltages are of opposite polarity, so their contribution at output node is going to be 0, and while RF voltages, they are of the same polarity, so as if they are connected in parallel and to the output node. So that is why the output voltage, therefore the output voltage VO is going to be equal to VRF. So now this can be written as 1 into VRF. So now we can write the complete output. The complete output for the two halves is 0 into VRF when VLO is high, and 1 into VRF when VLO is low. So here also we see that output is basically getting multiplied by square wave between 0 and 1. And VRF is A cos omega RFT, and this square wave is between 0 and 1. So this becomes product of RF and Fourier components of this square wave, which is minus 1 by 2 plus 2 by pi cos omega LOT minus 1 by 3 cos 3 omega LOT, so on and so forth. So our IF is going to be product of RF and the fundamental of the square wave. Therefore, VIF is A cos omega RFT into 2 by pi. That minus sign is also there. So this gives rise to minus a by pi cos omega RF plus omega LOT plus cos omega RF minus omega LOT. So therefore the conversion gain DC is equal to output amplitude, which is A by pi divided by input amplitude equal to 1 by pi. So this is same as that we have been getting for MOS based single balance mixers. So in terms of conversion gain, there is no advantage. Now, what about the feed through? So first is RF to IF. So we see that RF to IF will be present. This is RF, and it is able to reach to the output because of this DC. So in the output, we will see that A by 2 cos RFT term will be present. So this is present. Now what about LO to IF? So for that, we will have to see the circuit. So here we have LO, and we want to know whether it reaches to the output or not. So we see that in this case, in case 1, when LO is high, the output gets isolated from the input because of the open switches. So that is why this LO to IF is not present here in the case 1. Now in the case 2, uh, switches are closed here, but here we can see that the first path, the node A, contributes minus VLO, while the node C contributes plus VLO. So again, at the output, there is no LO. So here also we see that LO to IF is not present. So this is absent because the port is either isolated or it is connected simultaneously to the plus LO and minus LO. Now, what about LO to RF? So for that, once again, we will visit the two cases. So here we see that because of the same region, here RF is actually connected at the center of the secondary. So in this case also, there will be no LO2 RF because A and C, they are always of opposite polarity. So center will always be grounded. So this happens in the first half, and same situation is in the second half because here we have positive polarity, here we have negative polarity. So again, this center is going to be grounded with respect to LO voltage. So this is also absent. So we see that isolation is better in this case, although the conversion gain is same as that of a MOS-based single balance mixer. Now, when we converted MOS single balance to double balance, we had conversion gain and better isolation also. So here also we can just try to see that what is the behavior of double balanced mixer. So as the name suggests, there will be more number of balance port. So VLO was anyway balanced for the single valence case also. But in this case, the RF port becomes balanced. However, the IF or the output, it continues to remain unbalanced, that is single ended. And like that of the MOS case, here there will be more number of diodes involved. So we have LO here on right side, and on left side we have RF. And these windings are 1:2. Secondary is 2 and primary is 1. Because secondary you can see is in two parts. So center of the secondary of the LO is grounded, and the center of secondary of RF is used to take the output. And this output is single ended, so there will be load connected between this node and ground. So here we already have ground at C dash, so this is connected like this. So this is a circuitry of double balanced diode mixer. Let us name these diodes D1, D2, D3, D4. So here also we will consider two halves of LO, and for each half we will try to figure out what is the state of the two diodes, and then try to find out the voltage at node C, because that is the output voltage, and C dash is anyway grounded. So we are going to consider two cases, and here also of course all diodes act as switches, and VLO is large square wave. So first we consider case 1, VLO to be high. So now let us see that what will happen to these diodes in terms of their on or forward bias or reverse biasing status. So VLO is high, that means this is the polarity. So this polarity will be copied to A and A dash. So A is at higher potential compared with A dash. And since A is connected here and A dash is connected here, so we see that we have this polarity uh, between the diodes. So in this case, what we find is that these two diodes, they experience large forward bias. However, the other two diodes, they experience large reverse bias. So here we have forward biasing and bottom two diodes, they are reverse bias. So they are going to be D3 and D4, they are going to be open circuited. D1 and D2, they are going to be closed switch or short circuited. So what we now find is this implies D1, D2 forward bias, D3, D4 reverse bias. So this implies they are closed and these are open. So now we can redraw the circuit. So we find D1, D2, they are closed. However, D3 and D4, they are open circuited. And this is node A, this is node A dash. And this is center C dash, which is grounded. So if A is at certain positive voltage, A dash will be also of the same numerical value but negative voltage. Say if this is VLO, so this is minus VLO. Now we need to find out what will be the output voltage, which is voltage at this node C. So this is ground. It is also equal to C dash. So this output voltage is between node C and ground. So here we see the C node is here. So that means we are basically measuring the output between this node and a ground. And here what we see is this is node B, this is node B dash, and node B is connected to A and A dash of opposite polarities. So this node B also is grounded. So this voltage that we are looking across RL is actually this voltage. voltage of C with respect to node B. And what will happen here is we have RF here. So the polarity of RF, if it is like this, then polarity of B and C should be like this. And since we are measuring the node C with respect to B, so this BC voltage is going to be reverse of the RF polarity. So that is why VO is, which is equal to VCB, will turn out to be minus VRF. Keep in mind this is 1:2 winding. So
Excuse me,
BC,
sir. Sir,
yes,
how B grounded?
because you can see that node A is plus VLO while node A dash is minus VLO. And these two nodes, they have been short circuited because of D1 and D2.
Okay, sir, got it.
So D1, D2 has short circuited A and A dash, which are of opposite polarity. So we find that output is minus VRF. So we can write that VO is equal to minus 1 into VRF. So this is the story during the first half of LO. Now let us consider case 2. That means VLO is low. So what we now have is uh, just a reverse situation that of the previous case. So now we have this as positive polarity, this is negative polarity. So that means A dash is now going to be at higher voltage compared with A. In fact, if A dash is plus VLO, then A is going to be minus VLO, because its center of the secondary C dash is grounded. So that is why A and A dash will always be of the same magnitude but opposite polarity. So now what we see is A is negative and A dash is positive. So in this case, we will have a different scenario, just opposite situation that of the previous case. So in this case, we see that D4 and D3, they experience large forward bias, while D1 and D2, they are experiencing large reverse bias. So this implies that D3, D4, they are going to be short circuited, and D1, D2, they are going to be open circuited. Once again, draw the equivalent circuit for this case. So we now have D3 and D4 as closed switches, while D1 and D2, they are going to be open switches. So this is A node and this is A dash node. So here we have already seen that this is at VLO plus VLO, while A is at minus VLO. So let us complete this circuit. and this is node C, which is grounded. So this time we are looking for output voltage between node C, again like the previous case, and between ground. And here we see that node B is isolated because of open D1 and D2, but node B dash is connected to simultaneously A and A dash, and A is at minus VLO, A dash is at plus VLO. So that is why this node is at zero voltage. So this node B dash is now ground. So we are now reading the voltage of node C with respect to node B. So output is VCV dash. And here we have RF. And the polarity for these is like this. So here we see that the polarity of CV dash is going to be same as that of the polarity of RF. So that is why this is CB dash this time is going to be equal to VRF. So output is plus 1 into VRF. So now we can write the complete output. So complete output is minus 1 into VRF for the first half and plus 1 into VRF for second half. So this output becomes VRF into a square wave between minus 1 and plus 1. So keep in mind that we had considered VLO to be high uh, at t is equal to 0. So here we see that it is getting multiplied by minus 1 that moment. So this becomes therefore IF is A cos omega RFT into minus 4 by pi cos omega LOT. So in this case, amplitude of IF is going to be 2 by pi A. Therefore, the conversion gain is going to be 2 by pi, which is 2 times that of the single valence case. Now, let us see what is the status of feed through. So first is RF to IF feed through. So here we see that there is no DC. So that means RF will not be present on the output side. Now, what about LO to IRF? So for that, we will visit the circuit equivalent circuits for two half. So this is LO, and we want to know whether there is any LO that reaches to RF or not. So for this LO to reach to the RF, it must first reach the secondary of RF. So if it is able to reach between B and B dash, then it will always be present at primary also. So now what we see here is that what happens with B and B dash. So in this case, B dash is isolated because D3 and D4 are open. However, B is grounded because B is connected to A and A dash, which are of opposite polarity and same magnitude. So that is why LO will never be present between B and B dash, and hence it will never be present between the RF primary winding. So this is the story during the first half. During the second half of LO, we see that now B is isolated because D1 and D2 they are open circuit, and B dash is grounded because A and A dash they are of opposite polarity. So again, LO is not able to reach between B and B dash, and hence it will not be present on the primary of the RF. So what we find, LO to RF is also absent, and this is because of so they are BB dash either isolated or grounded. Now, what about the third important leakage? That means LO to IF or LO to output. So LO2 output means LO must be present at node C. Then only it could be present uh, at the output, or maybe at B or B dash. So we see that B is grounded, B dash is isolated. So there is no LO between B and B dash. So there will be no LO at C also. The region which prevented LO to get leaked to RF is also responsible from preventing LO leakage to IF, because IF is being taken from the secondary of the RF port. And since the secondary of RF is isolated from LO, so output is also going to be isolated. And this is the story in the both the half of LO. So this is also absent, and the region is same as that of the previous case. So advantage of this double balance is that this one is ports are well isolated, compared with that of the MOS version, and it can be used at high frequency. Now we will talk about the noise factor of down conversion mixer. So this mixer is encountered in receiver path. So here what we have is to find out the noise factor, we need to find the ratio of SNR, the output SNR to input SNR. Sorry, the input SNR to output SNR. So these are the signals that we encounter in this mixer, and this NO is the total output noise power at the output of the mixer. So this will have two components. One is that this input noise multiplied by the conversion gain of the mixer, and we have taken square because up till now we have been calculating conversion gain in terms of amplitude and the noise added by mixer. So output will have these two components. Now what we need to do is we need to calculate the input power, output signal power, and output noise we have already written here, and Ni is going to be a standard input power for all the cases. So let us calculate what will be noise factor when this input signal is single sideband or double sideband. So first we will consider case 1, that of SI to be input signal to be single sideband. So we know that in the single sideband, if this is the my message signal, which is the base band, then this is up converted and then transmitted. So after up conversion, we will usually have two bands, omega LO plus omega M. Here is omega LO, the carrier frequency, and its image, which will be suppressed in the single sideband, which is omega LO minus omega M. So this part is eliminated and only this thing is transmitted. So our VSSB is going to be A cos omega LO plus omega M T, where omega M is the baseband signal, message signal. So therefore, SI is going to be equal to A square, because A is the amplitude, by 2. You can include R also, or you can say that it is SI is going to be proportional to A square by 2. Now when this is down converted, we need to know what will be SO. So for that we have to down convert it. So for down conversion, we will multiply it with LO signal. So when we do the down conversion, what we get is our VSSB multiplied with cos LOT, and of course there will be conversion gain. So what we will get here is A by 2 GC cos omega MT plus cos 2 LO plus omega MT. So it is this VSSB which gets multiplied with LO. So here, after down conversion, we will have to filter out the message signal, which is going to be, so VO is going to be A by 2 GC cos omega MT. Therefore, the output power is going to be, this is the amplitude after down conversion. So square of this, half into square of this divided by R. So this becomes A square GC square by 8R. So this is the output signal power. Now we can calculate noise factor for SSB signal. So input SNR divided by output SNR. So we now know SI, we know SO, NO, we have already written general expression, NE is the standard. So all the four quantities are now known. So we can write the expression A square by 2R, this is SI, 8R by A square GC square, this is SO, NO is N GC square Ni plus N mixer, and Ni is the standard noise. So this, when you do the simplification, this will turn out to be 4 1 plus N mixer divided by GC square Ni. So this is the noise factor of SSB signal. Now for DSP signal, so we again have the same message signal at omega m, and this is then up converted, and in this case we will have both the halves, omega LO plus omega m and omega LO minus omega m. So our DSB signal is A into cos omega LO minus omega m t plus cos omega LO plus omega m t. So in this case, signal power SI will be A square by 2R plus A square by 2R, that of each of the two parts. So this becomes A square by R. Now after down conversion, that means when this signal gets multiplied by cos omega LOT, what we will get is A, and conversion gain, and each of these two parts, they are going to get down converted. So they are going to give rise to two terms. So in short, we can write so when we complete this thing, we are going to get four factors. So these are the four components that we will get. And out of this, these these two are the uh, components in which we will be interested. So VIF is going to be AGC by 2 into 2 cos omega mt. So this is AGC cos omega mt VIF. So we can now find out what will be the output power. So for DSB case is A square GC square by 2 R. So now we know all the four components. So noise factor for DSB input signal is SI by SO into NI, sorry, NO by NI. And this is A square by R, A square GC square by 2R into GC square NI plus N mixer divided by NI. So if we carry out this simplification, this will turn out to be 1 plus N max N mixer divided by GC square NI. And if you compare this with the previous result, we find that this is half of the F of the SSB signal. So this is for the noise factor. And if you calculate noise figure, then noise figure for DSB will be equal to minus 3 dB for half plus noise figure of SSB. So we see that noise figure of DSB is minus 3 dB or 3 dB less than that of the SSB signal here. And this happens, you can see graphically also, because so here we have a scenario for DSB signal. So in this case, there will be noise floor. So when this down conversion occurs, when this is down converted, in this case, these two signal components, they undergo down conversion, and that is why we get 2 cos omega t term. And noise at the location of both the signals, they also get down converted. So after down conversion, we get 2 signals and 2 noise. However, if you see the case for single sideband, then again we have noise present. Noise will be present throughout the band. So here, when this is down converted, what happens? Only one signal gets down converted. However, noise at the signal location and image location both get down converted. So what happens in single sideband case? There will be more noise at the output because noise from here and from here both will be present, will get down converted. However, only one signal component is present. But in the case of DSB, uh, noise and signal both are 2 times. So that is why the ratio for the case of SSB is more than that of the DSB case. So this is the graphical justification that why we have more noise factor for SSB compared with DSB case.